Alright, lesson 8 here is force on moving charges, and so there is a video which is a pretty cool video too, this one, so make sure that you do have a look at this one, because it really shows something which I will point out later. Alright, so previously we worked out a force on the current. So we did that before now, and that of course was F equals NILB. So for this purpose of this, I'm going to use N equals 1, so just one wire. So if there is just one wire, then that force would be ILB. Now, current is moving charges. Alright, so this here of course is important, but we're now developing with that, and current being moving charges. So current moving charges, and as we know from before, that the current is the amount of charge going past you every second, for example. Also, we know from our mechanics and our motion stuff that velocity is distance over time. So if we do that and the distance would be, the length of the field that it travels through, or over the time that it takes to go through that field. So if we do a bit of rearranging here, times both sides by, so you then get that VT equals the length of the field. So when we go back to this here, we can replace that and we can replace that. So when we go ahead and we do that, we get that the force is the current, which is Q over T, times the length, which is VT, times the field. Alright, now you'll notice that there's a T here and a T there, and one of them's on the top and one of them's on the bottom, so they cancel each other out. So what we then end up with is that the force equals Q V B. So the force is the charge times this velocity times the magnetic field. Alright, so we need to know the direction again, and so we use the right hand again, the right hand push, and this time with the right hand push we again point the fingers in the direction of the field. Let's whack another finger in there, and so our field's going that way. For example, our fingers point that way, our thumb goes in the direction of the velocity, and let's say the velocity is this way. So our thumb goes in the direction of the velocity, and the only way we can do that with our right hand is that we've got our palm pointing up. So the direction here of this is out of page. Alright, so both right hand push rules, fingers go in the direction of the field. Alright, so that's the key bit. Fingers in the direction of the field, thumb in the direction the other way, and whichever way your palm points is the way that we the force is, sorry, there's the direction of the force. Alright, now the other thing that I didn't mention about this here is it's the direction is out of the page, which is true, but that's for positive charges. Okay, so out of the page for positive charges. So if it's a negative charge, you still do the same, but remember, it's the positive charge is push for the hand, so it's the opposite direction for a negative charge. Alright, now this is quite interesting because if we have a look at this diagram, so this is a negative charge, fields into the page, and so let's look at this one up here to begin with. Fields into the page, so the fingers go into the page, the thumb points in the direction that it's moving at that point, which is in the tangent. Positive charges would be pushed out, but the negative charge is pushed in. And then when we do the same thing and we go around to all these different spots around it, we find that the force at all spots is pointing in. And because it's 90 degrees to the direction of travel, it's always pointing towards the centre. So an electron, in this case, is going to go around in a circle, which is quite interesting. So that's provided, of course, the field is big enough. Now, I said I'd get back to that video, so if you're looking at that video, the guy in there with some pretty fancy equipment at a university sets up, and you can actually see the electron beam that he's got in, and he's got, you know, this fluorescent gas, so that the electrons, when they hit that, they fluoresce, and you can see the path. You can see him actually set up a circle, so it's not just, you know, theoretical thing, it can happen. So if that's the case and we can get a circle, what radius is that circle going to be? Alright, so remember, so if there's a force acting inwards, and it's the magnetic force, or the electromagnetic force that's acting in, and if it's a circular motion, then that electromagnetic force is what makes the centripetal force. So let's have a look at those things. So our force of our electromagnetic, I'll call it the M, is QVB. Our F centripetal will be mv squared on R. And so it's this R here that we are interested in. So, of course, as I said, the centripetal force, not a force in its own right, but it's provided by something. In this case, it's the electromagnetic force that provides that. So QVB has got to equal to mv squared on R, and if we rearrange, so times both sides by R, divide both sides by QVB, you'll notice you've got a V and a V squared, so there's a cancel there, there's a cancel with one of those in the V squared. So the radius of the circle depends on the mass of the particle, the velocity it's moving, the charge on the particle, and the field that it's in. Alright, and so that there's handy, that's something you put on your sheet of notes and that, because it could be handy. Alright, so let's have a look at an example using it. Alright, so here we are, we've got an alpha particle of charge, so alpha particle is positive, right? And it has a mass, there it is, fired into a uniform magnetic field of 0.424 Tesla, uniform velocity east, so it's fired in the east direction. So first of all, it says what is the force on the alpha particle. So the force is QVB. So Q is the charge on our alpha particle, which is 3.2 by 10 to the minus 19, times the velocity, which is 8.0 by 10 to the 6, times times the field, which is 0.24 Tesla. And you stick all that in your calculator, and you go 6.1 by 10 to the minus 13. Oops, 13, not that, whatever that is. 13 Newton. Alright. So if you wanted to figure out the direction, point your fingers in the direction of the field north, your thumb in the direction of the velocity east, and when you go north and east, your palm pushes up, and it's positive charges, so that's right, palm pushes up. So the direction, if you wanted it, I don't think we better put it in because it asks for the force, and force is a vector, so the direction would be up. Part B is asking for the radius. Okay, so the radius, of course, is mv qb. So the mass, the information back here, the mass 6.7 by 10 to the minus 27. Times the velocity, which was 8.0 by 10 to the 6, over the charge, which was 3.2 by 10 to the minus 19, and then the field was 0.24. You put all that in your calculator, and you find it comes out to 0.7 of a metre. Alright, so that's that for some using charges. Alright, so the last thing we need to do with fields before we then move into a couple of areas which are applications is comparing fields. So here's a table, and this table's in your... Alright, so this is a table that compares things. There's also some dot points in there that tell you what similarities. So similarities is things don't have to touch. The direction talks about that. The uniform field would be with the lines are separated evenly. Static if it doesn't change, and around a monopole is radial, and it varies from the distance. Alright, and they're all talked about. So here's the fields, and here's the table. So gravitational, electrical and magnetic, and here's the thing. So the type of pole, there we go. Gravitational is always monopole, so there's always just one planet attracting stuff. Electrical could be monopole or dipole, so in other words, we could have just one charge, like a negative, or we could have both the negative and positive. Magnetics are always dipoles. Alright, type of force, what it does, the extent of the field, whether it just extends or you can make it smaller. Then there's couple of formulas about the strength of it, the force between, potential energy, and force due to a uniform field in that table. Alright, so there's some text questions, and then there's a bunch of past exam questions, quite a number of them. Alright, so you need to have a go at that and have a look at that and those things. There, of course, for all the exams questions, there's answers in the notes as well. Alright, so my notes, of course, are on the website. So there, if you've missed any of those things that fit into your gaps, you can get them. Watch the video, it's pretty cool. And if there are anything that you are not sure of, make sure you get clarification from me.